So the first one here, if hydrogen molecules and oxygen molecules have the same kinetic energy, then they will have the same speed.
Yes, it's ugly sweater day, but we have a problem to solve here. So kinetic energy is dependent on mass and speed. So even though they have the same speed, oxygen and hydrogen have different masses. So they will have different kinetic energies. And so just to run this by you quick, if I think about it, which one did we want to figure out? Let's say oxygen. So oxygen has 16 times the mass. So what's its speed going to be like? Well, in order to have the same kinetic energy over here, oxygen, I'm going to have to divide by 16, which is actually 4 squared. So oxygen will be moving a fourth the speed of hydrogen to have the same amount of kinetic energy.
Yeah, correct answer. False here. All right, let's take a look at the next one. Does the kinetic energy of a car change more when the speed goes from 10 to 15 or from 15 to 20?
All right, so as we see, kinetic energy is dependent on the speed squared, which means I have a parabola. And so for each increment in the x direction, it goes up different amounts the further along the x-axis I go. And so for that first section, it only goes up a little bit of kinetic energy. For that second equal rise in speed, it goes up significantly more during that next rise. And so this kind of leads us to the understanding that it takes a lot of energy to build that speed up more and more. This is why taking a rocket to outer space takes a lot of energy. And even if we extend this past speeds like that, and we start to think, well, what happens as I start to approach the speed of light, which is the speed limit of the universe? Why can't I go faster than that speed of light? Well, it turns out that this is kind of a parabola. At the start, it looks like a parabola, but in reality, there's actually an asymptote that it does not pass the speed of light, which we call c. And so in order to get to essentially that c, is we take the limit as it approaches the speed of light, the energy is essentially infinite in order to get there. And so we can't get there.
Correct answer there, 15 to 20, yes. All right, next one. Which of the following statements about work is true? Negative net work done on an object always reduces the object's kinetic energy. If the net work done on an object by a force is 0, then either the force or the displacement must have a 0 magnitude, or if a force acts downward, it does negative work.
When we're looking at work, when the force and the displacement are opposite directions, the work is negative, meaning it's removing kinetic energy and it's trying to slow that object down. If the force is in the same direction as the displacement, the work is positive. We're adding energy to the kinetic energy and it's trying to speed it up. And you can think about this in force is related to acceleration in that if the acceleration and the displacement, which is the direction it's moving, the velocity are in the same direction, we're speeding up kind of thing. Now, if the force and the displacement are perpendicular, that means no energy is being added or subtracted from the kinetic energy, and we have a constant speed. Now, I want to emphasize the word speed here, because the velocity, the direction can change because of this force, but the speed does not change. And so the correct answer here, negative net work is done on an object, always reduces the object's kinetic energy. Correct, that's what negative work does. It reduces the kinetic energy. If the work done on an object by a force is 0, then either one of them must be 0. No, we do have this option where they are perpendicular. So that one's not true. And then if the force acts downward, it does negative work. No, it's more dependent on the direction relative to the displacement. So if the force is down, displacement's down, positive work. Okay?
Yes, the correct answer is A. And again, remember that B one there. Yeah, we can't have them perpendicular. Consider two frictionless inclined planes with the same vertical height. Plane 1 makes an angle of 30 degrees with the horizontal. Plane 2 makes an angle of 60 degrees with the horizontal. Mass M1 is placed at the top of the plane and mass 2 is placed at the top of the plane 2. Both masses are released at the same time. At the bottom, which one is going faster? let's take a look at the board.
So which one's going to get to the bottom faster? So notice that when we set up our work kinetic energy theorem, we find out that there's going to be kinetic energy at the bottom, there's potential energy at the top. And so I go ahead, set up my problem. The masses don't matter, so that could be even another question with this. Does the mass of these situations matter? No, it does not. And I find out that the speed is just dependent on the height. So since they have the same height, they're going to have the same speed at the bottom now. I want to address some other things here. They have different slopes. So that means, are they going to have different accelerations? Yes. Are they going to have different distances along those slopes? Yes. Are they going to have different times? Yes. So acceleration, time, distance, all of those are going to be different, but the end speeds will be the same in this situation.
Right, they'll be both going the same speed because the only variable here is height, especially with that frictionless incline. A brick is dropped from the top of a building through the air. Friction is present to the ground below. How does the brick's kinetic energy just before striking the ground compare with the gravitational potential energy at the top of the building? Say y equals 0 at the ground level. All right, let's take a look at this.
So we do have air resistance here, meaning as that brick falls, that gravitational potential energy is being turned into kinetic energy. And when I get to the bottom, I shouldn't have any gravitational potential energy left. It should all have translated over to kinetic. But along the way, I was losing energy to friction. And so I'm going to end with less energy than I started with, or I'm going to start with more than I end with, however you want to say that.
So here it is. The correct answer is C, yes. For each of the two objects with different masses, the gravitational potential energy is 100 joules. They are released from rest and fall to the ground with no air resistance. Which of the following statements is true?
Okay, so we got our two objects. They have the same amount of potential energy, but they have different masses. And so if they have the same amount of energy but different masses, the only way to make that happen is either to put them on different planets, which they're both here on Earth, or to have different heights. So the different mass means they're going to have different heights. If I drop things from different heights, they're going to take different amounts of time to reach the ground. They're also going to reach the ground with different speeds. They will have the same acceleration, but they will have different times and different speeds because they have different heights. However, if I think about more of my energy equation over here, they have the same amount of potential energy to start with, so they're going to end up with the same amount of kinetic energy. And the reason they can do that with different masses is if I think about kinetic energy, it's 1/2 mv squared. So the different mass is okay because the speed is also different.
Correct answer there. Both objects will have the same kinetic energy when they reach the ground. You slam on the brakes on your car in a panic and skid a distance of d on a straight and level road. If you have been traveling twice as fast, what distance would your car have skidded under those same conditions? Let's take a look at the board.
So let's think about that. So my relationship here is that S is equal to v squared divided by 2 mu sub k times g. So the only way to change S is if I change the coefficient of friction, meaning the road's like icy or wet, or I change my speed. And if I go ahead and double that speed, essentially I've multiplied this side of the equation by 2 squared. So that means it's going to take 4 times as long for you to stop if you're going twice as fast.
So yeah, the correct answer here, 4 times that distance. Twice the speed, 4 times that distance. All right, last one. You wish to accelerate your car from rest at a constant acceleration. Assume that there is negligible air drag. To create a constant acceleration, your car's engine must.
All right, so we're looking at the power of your car as you go faster and faster. And so we're looking at the instantaneous power. So we're going to use that instantaneous power equation. And so the acceleration is going to be constant. Okay, so that number stays the same. But the faster you go, that means your velocity is getting larger. And so if your velocity is getting larger, then the power must be getting larger as well in order to maintain that same constant acceleration.
So yeah, it has to have an increasing power. C is the correct answer there. All right, that wraps it up.